So in these problems, we have something a little bit different. We are not talking about one gas changing. We're talking about one gas staying the same, but we're using a lot more information. So you're told in this first one, if I have 4 moles of a gas at a pressure of 5.6 atm and a volume of 12 liters, what is the temperature? So let's write what we know. Our moles are 4, and when using the ideal gas law, we use N to represent moles. Our pressure, and we don't need to give it a number because it's the only pressure, is 5.6 atmospheres. Our volume is 12, and we're asked to find temperature. We know PV equals nRT. We have P, and we have V, and we have N, and we're asked for T. R is a constant, so I listed them in your notes. You have to find the R that uses ATM. The value of R, the ideal gas law constant, when using ATM, and the reason we have to make it match is otherwise atmospheres won't cancel out, it's 0.0821 liters times atmosphere Kelvin times mole. So if we're solving for temperature, we can divide both sides. So if we're solving for temperature, we divide both sides by N times R. So our temperature equals PV over nR. So our temperature is equal to 5.6 atm times 12 liters divided by 4 moles times 0.0821 liters atm. Okay, there's more. Moles cancel out, atm and liters cancel out to give us Kelvin left for our temperature, which makes sense. So we put the rest in our calculator. 5.6 times 12 divided by 4 divided by 0.0821. And our calculator gives us 204.629. And if we think about significant figures, we have 2, 2, 2, and 3. So when we round our answer to have 2 significant figures, we have to put it into scientific notation. And to get 2.0 times 10 to the second Kelvin. Let's try one more. So this equation says I have an unknown quantity of a gas at a pressure of 834 kPa, a volume of 31 liters, and a temperature of 87 degrees Celsius. How many moles do I have? So we know we're solving for N, and we're given that pressure equals 834 kPa, volume is 31 liters, and temperature is 87 degrees Celsius. If we're using the units kPa for pressure, then we have to use the value for the ideal gas law constant that has the right units. So 8.314 liters times kPa divided by mole times Kelvin. We should make sure that our volume and temperature in the right units. Our volume is liters. Our temperature is Celsius, but we have to have Kelvin. So when we add 273, we get that our temperature is 360 Kelvin. Our equation, the ideal gas law, is PV equals nRT. And to solve for n, we divide both sides by RT. So n equals PV divided by RT. So we can plug into our equation down here. 834 kPa times 31 liters divided by 8.314 liters kPa times 360 Kelvin. Kelvins cancel out, kPa cancels out, and liters cancels out, which gives us moles for our remaining units. So we do 834 times 31 divided by 8.314 and divided by 360. And you get 8.63804. For significant figures, we have 3, and we have 2, 2, and 4. So we're going to round our answer to have 2 significant figures. So we get 8.6 moles.